Okay, so I was talking about that when you stretch a coil, okay, the length or volume, like coil is like a spring. Okay, so when you just imagine that you are stretching a spring, so the length and the volume of that string doesn't changes in the material, like length doesn't change. If you stretch a rubber, the material changes, it elongates, but like in steel, if you if in a coil, like if you just stretch it, there is no change in length, there is only change in shape. So when there is change in shape or little deformation, like this, if I explain here, I am using the slate pen, old fashioned but still, like if this is a cylinder and it gets deformed by this and not from this, like only a change in shape, so it's a shear modulus. That's what all this right. Okay, now next. Okay, so what's here, it's given here, the figure is already drawn, so I doesn't need to draw. Here two wires are given and a diameter are also given, one is of steel, another of brass, and they are loaded by some of the weight, and the mass of the weight is also given, and the length of the steel and brass before loading, like that original length, that's L, not delta L, it's given, and and the Young's modulus is given. So we have to find the elongations of steel and brass wires. So it's a simple formula based question. So first we find of steel wire, there is length, radius, we are given the diameter, so upon 2. Then force is equals to 6 plus 4 by, because this steel wire 6 is for this and 4 is for this, and force is equal to mass into acceleration, so mass into gravity, that, then Young's modulus, then as per the formula, and we shift this to this to this, and we get this, and this I have done to all the calculations here. You can pause the video and see the calculations more, like from here it's simple mathematics, but the one-to-one calculations are done. Okay, for brass wire, length is given, radius, force is equal to mass into acceleration, then this modulus is given, Young's modulus, and then simple. You now see this, the edge of an aluminium, like here what is this. Okay, so it's, I will explain here by simple drawing. So here it's a wall, and from that wall a cube is attached, like from here, from this face only this cube is attached. Okay, so this face only, like if I say a cube, so like this, if this, it's a cuboid, but consider this as a cube, so this face is attached like this on a wall. Okay, and from here, like if we just take a straight rod and if we just put a mass of here, like that's, it's there. So when I put the mass, it's that vertical deflection, it gets a little downwards. If I put the mass here, it gets a little down. So you have to find that delta L. Okay, that's a simple formula based question. Okay, so area of face, area is equal to 10 into 10. Why would 10 into 10? And as the area of cube is 6L square, but we have taken L square. Why? Because only the force is applied on this area only, on this part of the, in this face only, like on this square, like on this square only. So that's L into L, that's why this area. So we get this, force is equal to mass into acceleration, that's gravitation. Okay, we found this. Then the modulus, what is G here? G is nothing but giga. Giga is 10 raised to 9, so 10 raised to 9 pascals. So that we have to that we will get in pascals. Length, you all know. Then this shear modulus is equals to F upon E into L upon delta L, and we get this from, we shifted this from here to this here, and we get the answer. This I have done the calculations. Now next here drawn, like, so here 4 cylinders are taken. On those 4 cylinders a mass of 50,000 kg is put, okay, and the cylinders are like a hollow cylinder, means how you consider a bottle and all, like this, a hollow cylinder. Like this is a simple hollow cylinder, but if you just get like this, so we get this all part like this, okay. So it's given like this, and the inner diameter is 30 centimeter, outer is 40 centimeter, and the Young's modulus is also given, and we have to find the strain, like at what strain they get compressed, okay. So first I got radius and converted into meter, because everything, because Newton per meter square, that's why. Then radius 2 per meter, then gamma, then as load is distributed among all, so we have to find load per one cylinder. We have to consider one cylinder, so that's upon 4. So this is the mass for one cylinder. Force equal to mass upon acceleration, mass into gravitation. That's the area of cross section of each column. So pi r square 2 minus pi r square 1. Why pi r square? That's the area of circle, because it's resting only on the circle. Only this circle is effective, and only this part is effective, not the hollow cylinder. This part is effective. So only that part is considered. So we have taken pi r square of radius 2 minus pi r square of radius 1. So we have taken common around calculation, so it gives 0.22 meter square. Then strain. What is strain? Strain is equals to, like, Young's modulus is equals to stress upon strain. So strain is equals to, we have written in very small, maybe you can see, stress upon strain. Then this is stress upon modulus is equals to strain, okay. So we have to find whole strain. We don't have to find the delta L or like a whole strain, okay. So force upon area, that's stress upon strain. Force upon area divided by this, so force upon area into reciprocal. That's how we can get this calculations. It is so easy. A copper is pulled, like this is a copper, this is pulled like this, and the force is given, Young's modulus is given. You would only find the strain. So force area is also given. So Young's modulus is equals to stress upon strain is equals to F upon A into strain, as we have discussed earlier. Here it is also written nicely. Then strain is equals to force upon A gamma, and I have done the calculations. This is also easy. Sigma, the stress equals to force upon area. So force is equals to area into stress. So here maximum load is considered as this, and that's how we calculate it. And I will do others tomorrow. Thank you.